Okay, folks, we'll go ahead and get started. Let me go ahead and open up in prayer, and I'll give you a sense of the things that we're going to be covering today. So, dear Heavenly Father, thank you for the chance to be working with each of the students in this course, Lord, as we get a chance to have an experience of a day in the life of what it would be like for being a systems engineer. And I pray that you would help each of the students in this course, Lord, that they can get clearer and clearer focus on what they would like to be doing in their future, and that you would open doors for them to land the career of their choice. I also pray, Lord, that you would help them in their spiritual formation, Lord, that every time they get a chance to be studying scripture, a lot of times here at APU, with folks that have been doing it for quite some time, that they can get a better sense of the messages that are there, and also the theological concepts we can draw from that and use in our day-to-day life. Give each of us some interesting and creative ways for faith integration. In Jesus' precious name we pray. Amen. Okay, well, like I said last time, we've made it through all of the chapters in our textbook. And so what this does is it gives me a few lectures at the end now to start to think about a little bit deeper about the type of projects that a system engineer would do. And I'm going to continue to be going along that line. I'll be talking about a specific NASA mission in just a minute. And then at the end, I just wanted to allow us to have a conversation about our projects, and we'll keep doing that until we actually have our project reports in the near term. So we saw all of these various steps that we take. And remember what I said, like a system engineer, one of the key things they have to be doing is thinking. And I remember a manager colleague that I used to collaborate fairly closely with, and he says a lot of people don't think. Now that sounds kind of interesting, and maybe not the most flattering thing, but it's one thing to say, okay, I'm going to have this or that for breakfast. It's another thing to really think through what is it that is needs to be done, and to come up with a rational argument of how to press forward with that. And so some of the skills, the system thinking mindset are things that can be quite useful. And so we're going to get a chance to be thinking about that here. And so I'm going to focus on a different presentation. Our last lecture, I went through something different, but this is now a mission oriented. And so Delegati was a person that we looked at with his Dell 77 model. And there he talks about the Holman transfer going from one orbit to another. And so I'll come back to that a little bit later, depending how our conversation goes with our round table after I finish up with this. Well, now we're going to be looking at a specific mission. And so this is what's called Radio Aurora Explorer. And so I'll explain a little bit more what that is. And so basically NASA, the National Science Foundation, and there's other tools that get coupled together to help them get the modeling and the analysis to figure out how they would proceed, what's the best option. So this gives us an idea of thinking about modeling and simulation for a CubeSat mission, where we're looking at model-based system engineering, behavior modeling execution, and it integrates a lot of different tools. And so Magic Draw, so the Cameo systems modeler, also the other tool that is interoperable for some of those things, the system of systems architect that I have. There's also something called the Cameo Simulation Toolkit, and that is a module that I've been able to demonstrate with you. You can actually go through the logic. I showed you a different tool that wasn't STK, but has the same kind of functionality, where we can be doing orbital analysis and getting some interesting calculations. I think now most of you are familiar with MATLAB, and the time this was developed, they were using something called Model Center. There's also something called a Stateflow, which is a module that I've used to do something that is in that area of what we're trying to accomplish here. So we think about a specific mission. And so what we're going to be talking about is how to use a model-based system engineering to design and assess a CubeSat mission. So here's a little bit of background of what that is, this Radio Aurora Explorer. And so this is the first National Science Foundation sponsored CubeSat mission. And so interesting enough, and so this has been something that has been going on for a while. And so the RAX mission is a joint effort between Stanford Research International, or SRI, and so this is in Menlo Park. And so it's like a think tank that has history related to Stanford University. And so it's relatively close to them. And so, and also they have a University of Michigan in Ann Arbor, Michigan. So the chief scientist at SRI International, Hassan, led the SRI to develop the payload. Okay, so there was a distinction between the payload and the bus. And then the chief engineer, James Cutler. So notice that they're presenting him as a chief engineer rather than a faculty, although you could say he's dual-hatted, led students to develop the satellite bus in the Michigan Exploratory Laboratory. So they have been doing this. They have a laboratory, and now they were developing a bus, and they now need to be working with another party. And all of that is a good thing. And so some folks may end up wanting to work there, say folks that were at Michigan. And so there's actually two CubeSats that were developed roughly about a year apart. And so RAX-1 mission was launched in about a little over 10 years ago, was a demo of the team's technological capabilities, and it made great strides in CubeSat design and was also able to execute bistatic radar measurements. And I'll have a chart on the next slide to talk about that a little bit more, that had never been done before on a satellite of its size. So we're using a CubeSat to doing some scientifically significant mission. So I think most everyone is familiar with radar, at least in terms of the general concept. Well, bistatic is a nuance to that, and I'll have that in just a minute in the next slide. So they built a second CubeSat, building on the heritage by completing the scientific portion of the overall mission. It is a reflection of students learning from practical experience. So they worked on the RAX-1 mission, now they're working on the RAX-2 and implementing new, more innovative technologies firsthand. And so we talked a little bit about that in terms of the life cycle of what happens in system engineering. So you have operation and support, and some of this starts to fold back towards the next generation as you think about what you're going to do. Any product, typically, if you're going to build more, you're not only going to build it to print, but if there makes sense to actually improve its capability, you're going to do that. And so this is what these students got a chance to be working on, as well as SRI. The RAX team members were able to get practical spacecraft troubleshooting experience. And so guess what? Not everything goes exactly as planned, and applied lessons learned from RAX-1 and RAX-2, which performs the same mission concept with improved bus performance and additional operational modes. So both of them saw what happened with RAX-1. They gave feedback. And so in this sense, they were their own boss, although ultimately the National Science Foundation, NASA, were providing the resources to help them along. RAX-2 launched about a year later as part of the NASA, this mission here that's listed. So this was just a summary to help you think of for a radar. Basically what you get is, so this is just a picture of one of the radar that you would see near an airport. And if you've ever gone by, you would see this rotating device. And so what it does, it sends out an electromagnetic signal, and it comes back to the same antenna, goes into this receiver, and they process. So you ping, and then you wait and see how long it takes for it to come back. Well, what a bistatic radar does, instead of having it ping going back to the same source, you actually ping and that actually goes to a different source. So the mathematics is a lot more complicated, but at least gives you an idea. And so the RAX is a ground-to-space bistatic remote sensing experiment designed to measure and understand the cause of meter scale ionospheric irregularities. And so meter scale gives you an idea of the fidelity. If you had a larger receiver, you would have more fidelity than that. But for some of the things that they were doing, just to be looking at the ionospheric irregularities. And so they're looking at things in the atmosphere. And so say you're illuminating it with some radio frequency, and it's going to bounce around and it's going to be received by this CubeSat, and that's going to be processed. So that just gives you an idea what's going on with this mission. So you can see, even in these steps that I've started to talk about already, okay, it's going to be a CubeSat. What are we going to try and demonstrate with this CubeSat? Okay, developing the partnerships, working out lanes of responsibility, a work breakdown structure, coming up with the high-level requirements. All of this are things that start to come together. And so model-based system engineering was applicable in 4 CubeSat phases. And the first phase was you have a working group that what they did is they created a CubeSat reference model, and this is something that's available in the NCOSE website. And so it was applied to a mission. So here the RAX mission was a 3U CubeSat. So what a 3U means is it's 10 by 10 by 30 centimeters. So it's 30 centimeters in one dimension. Well, it was this joint partnership with SRI and Michigan, so with the University of Michigan. So that was the first thing, is they started to create a model. The second phase focused on expanding the RAX CubeSat model to include modeling behaviors and interfaces with several commercial off-the-shelf simulation tools. We'll get to that in a minute, but this is where we get this long list of things that are out there to try and not only just capture a rough idea of a design, but kick the tires a little bit and see actually if we're on track. Does this logic make sense? So the third phase was comprised of 2 activities. The first was the development of the CubeSat enterprise model to capture cost and production life cycle aspects for the mission, spacecraft, and problem domain. The second activity incorporated additional design and operational characteristics into the RAX model. So you come up with a model only, then you start to look at the behaviors and the interfaces. Now you're starting to get into the cost, the life cycle cost, and getting a little bit deeper. And then finally, the modeling effort started anew in the 4th phase. The objective is a generic CubeSat reference model to provide a model that other projects can use as a starting point for their mission-specific CubeSat mode. So let's pretend that you are working for an aerospace company. And so you did something like this, and then you have a model that's actually gone through this whole thing, and then you genericize it to a degree. And now, the very beginning, you can hit the ball running with a model-based system engineering model that you can be using for your project. And so those are the things that were captured. And so this presentation is an aggregation of a lot of different sources. And so that was one of the things that came out. Okay, I won't go through this in as much detail, but this is giving a chance to be thinking of the motivation, what were the challenges, and so what would be the traditional system engineering approach with the focus on subsystems. And so this can be oversimplified, low fidelity, neglects the subsystem interactions, the requirement verification, uses averages, best and worst case scenarios. And so it's not as dynamic, so it's not capturing all the dynamic nature of missions. Models and simulations are not integrated. And so they're, quote, hacked together for one-off cases. They're not modular, extensible, or reusable. And so why would that be the case? Of lack of integrated modeling and simulation tools to enable system engineering, design, and analysis. And so that's what was there. So particularly an issue for CubeSats, and so this is just a reminder, a 1U is a 10 centimeter cubed, and it's less than a kilogram. Is it the physical components are physically integrated, it's extremely constrained. I think all of you at least have an idea what a 1U CubeSat is, or you may have actually held one of our models of that we have in our lab. And so it's extremely constrained in terms of power as well. So the operational constraints and decisions are coupled. When to collect data versus download the data. So when is a ground station going to be in the line of sight? How much power do you have? Are you going to do it all in a bursty mode, or are you going to trickle it out over time? So there are a variety of unknowns and dynamics that are out there. There's little or no control over the launch orbit. So this is where NASA comes in. It can provide a free launch to some. And so you just have to live with whatever you get. And the experience variation in eclipse duration may be another issue that comes out. And then you have to operate in inefficient type of environments at times. And so integrated models and tools are critical to design and plan for these missions. So why model-based system engineering? It's a formal, accurate, and authoritative single source. You guys now have some familiarity with that. It contains elements, relationships, and interactions. It's more than just having a piece of paper that you've written things together. It's an entity of the relationships as well as the components. There are multiple compatible views that explore physical and functional capability. And there's also things that are laid in there for requirements verification and traceability. So it enables integration of modes and simulations. So you can connect to other tools. And so here I'm showing you STK and MATLAB. And so there's ways of doing that. I'll have some blow-ups of these in a minute. You can execute dynamic simulations of end-to-end missions. You can identify failure to satisfy requirements, and think about maybe suboptimal designs. Saying you have multiple things you're trying to optimize, that's hard. And so maybe everything has to be a little bit suboptimal. It accommodates reevaluation when the design changes occur, and it enables co-simulation. That is simultaneous vehicle and mission design. And so you can be trying to do a whole lot of concept development on multiple fronts. So the RACS CubeSat mission, there are various ground stations that are available. And so roughly speaking, we would be having things in Japan, in Australia, various places around the United States. And so this is what this Cartesian view is trying to give us a sense. And so they have an experimental zone in Poker Flats, Alaska. And you can see that there's like triple coverage that we have here. So that actually would be a sweet spot for them to be engaging. But there is a global ground station network. And there's also the constraints on the vehicle, solar panels. There's only so much surface area for solar panels. And so if you're going to have everything body mounted, that's going to be a constraint. How many batteries are you going to stick in here? And what is the maximum amount of data that you can store? And then buffer that for when you actually have a link that you can send it out. So this is a blow up of an image looking at this mission, and I don't have the actual simulation they did in STK, but this just gives you some of the ideas. And so you can be seeing the orbit of a CubeSat there. That's one thing that shows up. It's then has this line below it is like the ground track that it's going that it's following. So you have this three-dimensional view that you can kind of rotate a little bit so it's not right on top, so you can distinguish those. And now we can be seeing this this operational zone that they're targeting. And so just trying to give you a little bit of insight of what now they're not just using Magic Draw, they're using SDK, they're using MATLAB, all of those things are there. So here are some of the operational CubeSat mission goals. And so develop a fundamental system model of the CubeSat mission, and then execute realistic behavior CubeSat scenarios. And so they're going to be designing scenarios. Each one of you is developing a project. And so you can be thinking, here are like 3 modes that you're going to have to be operating in. And so how are you going to go about doing that? And so getting a good understanding of the mission, we talked about use case diagrams, that can be helpful, then starting to write that up, and then figuring out what does that infer in terms of structure, function, relationships, requirements, and traceability. And then for the realistic behavior, you want to capture the operational opportunities, state evolution, mission performance. All of those things have to be thought through. And some of the diagrams that we have in SysML, which I've been able to show in a execution mode, has given a little bit insight into what that would be all about. So what would be the project deliverables? You have a system level SysML model, and this is in Magic Draw. And so the 2 ones that I have been showing are in Magic Draw, and I was able to import it into the tools that I have. Unfortunately, there's not a way to be doing this directly in Visual Paradigms. There's also the analytical models for describing the behavior, and this is where it can get into some other things that there needs to be these interfaces. But for the model, it can help us with the structure of the mission, architecture and vehicle, the requirements. It can help us with the constraints, and so we can be looking at things with parametric diagrams. And so this is something that you can be exploring with an analyzer. So if you have to trickle things down at 10 bits per second or 100 bits per second, how long is it going to take to clear your buffer? That would be an idea where you have a constraint and then you're trying to answer a research question. So behavior diagrams can capture the dynamic operations. And so those are some more things to be thinking about. So for modeling philosophies, we're looking for modularity. We want to be reusing the libraries of parts. And so that was a 4th phase that they were looking. They were looking at patterns. And so what were the modeling patterns that come up? There's a concept called design patterns that's more well thought through in the software side, but there are definitely things that you could be seeing with the hardware side or engineering side. And also nomenclature, trying to have a simple and sufficiently descriptive way of capturing all the things that you have in your design. So here is the CubeSat system model architecture. And so we can be seeing various views. And so we'll have a few blow-ups in a second. And then we can be having a parametric diagram that actually has conduits to SDK. So that would be something if you have a space mission. It could be something else if you had something other than that. And also MATLAB, where you have a lot more computational capability in a tool that's been around for quite some time. So here is the block definition diagram. And so this is just an idea of what it would look like. And so this is something that eventually was folded out into a standardized CubeSat kind of model. And so this is looking at the mission, not just the CubeSat itself. And so this was one of the ways that we got a chance to see how block definition diagrams could be used. Now we're looking at the specific vehicle itself. And so we have a blow up of all these boards. And so they have a 3U CubeSat, so they have more real estate than we would have in a 1U. And then we have communication, power, the payload, data management and all of the bus, all of these things are laid out in blocks. And so there's blocks that are related to the overall structure and then components at those levels. And you might remember in visual paradigms, you could actually show the parts that would be associated with a higher level block. They're hiding that in this diagram, but that's just another thing that we've got a little bit of a chance to experience. Well, now we have a block definition diagram, and we're starting to annotate requirements and show a relationship between those. And so this is something that you could take from your database of things that you've already developed it, and then illustrate it here. And so now we're showing satisfied relationships of different requirements. Remember that a requirement is supposed to have a shall statement. And so all of these have shall in them. So those are well defined the way that they're laying out their requirements. Now we have this parametric diagram, a blow up. And so then it starts to be talking about the tool that they used at the time was a model center, which was an interface that allowed you go to directly to STK and MATLAB and define specific scenarios and find out how it would work under these various kinds of configurations or things that you might experience. And so you can have a nice robust set of possible ways of how you can be looking at your system. So this is a blow up of the model center that where you have STK and MATLAB plugins. And so we get into the specifics about what parameters are going to be passed to MATLAB, and then they're going to compute those, and then you're going to have those that you can think through in a lot more detail. Here we have the satellite systems toolkit. I'm used to calling it a satellite toolkit, but now it's gotten a lot more capability. So you can call it system toolkit. So it's an analytical simulation tool to propagate orbits and compute the solar state, the access to experimental zone, and to the ground stations. And so here we can see this is the experimental zone here. It's also showing you the ground stations. So there's one in New Zealand, one in Australia, one in Japan, and we have 3 in the greater United States. And here is where we have the field of operation. And so we can be seeing that, well, you also have to be operating through an eclipse. So that means you're totally on battery power. And so when it's yellow, that means that you're in the sun. And so you want to be using the power then and also recharging your batteries and making sure you don't have the depth of discharge low enough that your batteries are not going to be able to come back with this amount of orbit to charge. And so that just gives you a power related study that needs to be explored, one of many things that need to be thought through. So we can have, like, each one of these constraints is something that we would want to be exploring. Well, what is the things that relates to, and are the requirements right, or we need to finesse it a little bit? All of those things can come up as we're progressing through our development. There's a parametric diagram solver. We don't have something like this with the tools that we're using in this course. And so this can be yet another way for us just to getting a better picture of what can be done when we have more resources, more individuals, and a larger time. We have only 1 semester to be computing everything that we're trying to accomplish in what we're doing. What this can show is we can see like a green that it passes, red that it fails, say yellow when it's marginal. I showed you a video with something like this going on, and was starting to do some of those annotations with a model of my own. And if we have time, I can continue to go back to that, but at least this is just giving you another level of exposure of what you can be doing with model-based system engineering. So bringing the model together, and so we can be seeing the state machine diagram here. And so this can be something that can be executed, and you can just be seeing if your states make sense. Do you have everything? Is there another state that you haven't captured? And so now, without investing a lot of resources, you can be doing these things at a higher level, and that can be a useful thing to be thinking about. Here we're looking at an activity diagram. And so this is used to be giving us some insight into the main simulation loop. And so this should be familiar to you with some of the things that we've talked about, and you've had a chance to be exploring that with your own activity diagram. This is the state update activity diagram. And so how does it transition from one state to another? And so now we're thinking about the process of that. And so we have another activity diagram to be helping us out thinking through that. So we have a lot of things that need to come together when we're going to be doing things at the mission level. And so say we have some of these lower level things, like I mentioned, the batteries need to stay charged. And when you're going through an eclipse, you need to be downloading the data with a certain constraint in the data rate. And are you going to be doing it a trickle mode or a bursty mode? Those are just a couple of things that start to come together when we're put it at a higher level. Can we actually do this mission? Can we perform this mission for a year with the resources that we've allocated to put into this CubeSat? Is the antenna large enough? We can get our link budget for the communication to work out, and just lots of things. And so now this just gives us where we can start to be looking at the results. For here, we're showing 11 different scenarios and see how it would work for all of that. So this is really hard to read, and I'm not going to be briefing in detail. We just wanted to give you a perspective to be thinking about that. We can also, we can be looking at the mission simulation results. And so here we can be looking at the depth of discharge of the batteries. And so here we have a solar eclipse, and we can see that I'm just going to give a number. I'm not going to try and read this, give it a precise number. Say it goes down 25% in the amount of charge that's there for this eclipse. And so the eclipse, during eclipse season, sometimes it'll be very large. Sometimes you won't have any eclipse at all. But this is one of the things that would need to be thought about. And what about the energy drop when you're actually doing a download? And so is this a bursting mode or a trickle mode? We can see there's a little bit of drop, even while you're still getting energy illuminated on your solar panels. And so you have a load, as well as stuff coming back into your batteries from your solar panels. And so that is another kind of a scenario and analysis that we could be doing. And then finally, even before we build any hardware, we do the requirements verification. Okay, are these requirements where they need to be, or do I need to adjust things and finesse things? And so thus we see some potential, several things that I've talked about where there can be a lot of cost savings as a result of going through this process. So this is just some more details looking at the battery capability, capacity. Do we have enough solar, enough battery cells to get us through the missions that we need? Or do we, maybe we could actually even take one off and then have some other kind of capability, more allocations for something else that might be important. So those are just things that could be thinking about. What would be the ideal orbit? And so are we going to be going for a low orbit, or are we going to be having a little bit higher? The higher the orbit, it's going to be over a certain area longer. So it's going to take it longer for it to go around one loop around the Earth. And so this just gives us a way we can start to be thinking about that. Or maybe you don't know exactly what orbit the International Space Station or some other asset is going to launch you into. And so you have to be prepared that you can go for a range of orbits and make sure that every one of those would be adequate for your needs. Now we can be looking at the ground station location. How long are you going to have access to each one of those ground stations? And so say one of these goes down for servicing, would you still be able to download everything with two ground stations? Or are all three needed? And if so, that could be a driver that you need to have more extra capabilities of the ground station. So if one part of it goes down, another part has to go up, so you maintain that connectivity. That's yet another example of a system engineering trade that would need to be worked. So what was seen in the project experience, and how did model-based system engineering help the team to overcome their challenges? The coupled and analytic models with simulation capabilities, you could very quickly, without a lot of cost, get a sense to what's going on. You were able to demonstrate behavior with the models. You were able to achieve requirements verification even before you built any hardware. And you saw the extensible ways in which you could use standards, libraries, and patterns. The lessons learned that working with many tools is challenging. And on the vendor side, some folks are trying to become super vendors and you can just buy everything in-house. Some of these tools are extremely expensive. And so that can be something that is a consideration. SDK has a lot of flexibility, but it's very expensive. And so you're seeing that word again, and it's best to automate repeated tasks. Working with vendors is necessary and advantageous. And always ask, am I using the right modeling and simulation tool? Another trade. What are the right tools for me to accomplish what I need? So sometimes an expensive tool, if it takes you 10% of the time, would be a good trade. And so there's all kinds of things that you need to be thinking about. So this is the last chart, and then there's just a credits chart, and I'll show that for a minute. And so in the future, their goal was they would want to extend the system level model. So they had one case for the RAX-2, and there's a lot of things that are on the docket for future missions. You want to extend and refine the behavior and analysis models. They got a baseline. You can always make things a little bit better. They wanted to work on automating system and mission parameter trade-offs. So if you have a whole lot of scenarios, that can be time consuming. And so the more automation you can do, the more robust you can be able to, with your digital twin that you have with your model, start to flesh things out. And finally, there is a desire to generalize the model for applicability to a variety of mission concepts. And so there were a variety of team members. JPL, part of NASA, was included in this. There was the vendors that were part of this. There was the folks from University of Michigan. There was a SRI and other folks that were helping out with just putting together the details of what they have in this presentation. So let me pause and see if there's any comments or questions that are, or if you're tracking it, you can also just do a thumbs up that you follow what we accomplished with covering that presentation. Okay, good. So like I said, I'm just trying to give you a larger context where we can start to do things. And so I'll just spend maybe like just a few more minutes going with our Magic Systems of System Architect. And so we have our Cameo Systems Modeler, No Magic, Magic Draw. We have Magic Systems of System Architect, and there is overlapping capability between each one of those things. And so some of these diagrams I've shown you already, but I'm just going to make a few more points. and then cut it over that we can have a conversation. So this was a packaging diagram, which can be helpful for us to see what the overall model and what is the hierarchy that's associated with this. And so the Delsat 77 is a generic small sat design. One of the things they highlight was this Hohmann transfer that I got a chance to be mentioning a little bit before. So here is a block view of the satellite. We've seen this, and we also had another example of this of a block diagram that's used to look at a satellite when we were looking at the RAX mission. So we can see how there's multiple layers. And so there's parameters that start showing up that you relate to a block, and you can either choose to have them, and so you can be showing the parts. You can just be showing other values that are associated with that. That's all with what's there. So parametric diagram is good for constraints. And so there's only so much propellants that you can send out through a nozzle at one time. And so you're trying to calculate how long you need to burn to get a certain delta V to go from one orbit to another. And so this just gives you an idea of one of those diagrams that would be helpful for that. We talked about the use case diagrams. And so say you're going to be looking you're going to be doing a Hohmann transfer. And so this is just one of several types of commands that could be taking place. So a payload operator is going to be focusing, say, like on the RAX mission, when are they going to be turning on and collecting from their sensors. This would be a different function. So this would be the payload, the satellite itself, making sure that it's in the right orbit. But all of those are examples of send commands. And so we see that can be captured as part of their design. So this gets into a little bit more details, but using a block definition diagram for a Hohmann transfer. And so these parameters here are ones that we saw on this diagram here. So you can be seeing some relatedness between those things. And I'm going to play this in a minute. And here are just the requirements that are associated with a Hohmann transfer. And I showed you this before, but here we can see these kind of complicated allocation matrices that are one of the things that now we're getting more into the details that we can be exploring. So I actually ran this before class, and I don't have the time to troubleshoot why it exactly doesn't complete totally, but I'm going to go ahead and leave it as is, because that could be an example that, say, maybe something in your logic is not quite correct. And so what I'll show you is that this first part works, that it can determine whether or not it's a valid command. And then it gets ready, okay, I'm ready to do a delta V maneuver, but then it gets stopped here. And so say something's wrong with this logic, but this is an activity diagram that I can start to be looking at, well, do I have things well conceived or not? And so I'm just going to go ahead and play this. I have this at a slow speed so we can walk through it in a better fashion. And so we get started. This is the node to start, and it does two things. It's validating the command, and it's also going to be measuring what its current altitude is. So this is complete. It's now measured what the altitude is. Then we have this validate the command. And so is it valid or is it not? And we have a decision diamond here. And so we're going to have a couple of commands. And I'm going to say, well, I'll do this one first. I'll say, yes, this is invalid. It says, okay, that means that it's invalid. And so then it's going to generate the response. And so there's going to be a telemetry response that is going to be passed out down to the ground that says, I'm sorry, but that's an invalid command. Say something got garbled. Okay, and that's a terminal mode for what we have here. So I'm gonna have to reset this, and I'm gonna start it again, trigger it. So we'll go through those same things, but this time I'm gonna go through a valid command. Right, we have our decision diamond here. And no, it was not false. Is it true? Yes. So that's a valid command. It's going to generate a response. That's going to go down to the bottom here like we did before and says, yes, okay, I got what you wanted to do. And I'm going to be sending it down. So that's going to be transmitted. Then after it's done that, it's going to go ahead and start to do the setup for a Holman transfer if one is required. And so this is where it gets stuck. And so I'm just going to leave it at that. So if it gets stuck, that means that your logic is not quite accurate and there's something that needs to be done. Any comments or questions on that? Or are you following along with what I did there? We introduced the Holman transfer on Tuesday, and so now I'm just following through with that now. You can just give me a thumbs up if you guys are tracking what I did. Okay, what I'm going to do at this point is I'm going to stop the recording, and then we can have a conversation. Let's talk about the details of our projects. Thank you.